Hello everyone and welcome to another video in the three-phase circuits course. In this video and the two subsequent videos, we are going to cover the unbalanced three-phase systems. Specifically in this video, we are going to cover unbalanced delta and star load while the star has a neutral wire. So let's start. So what are the outcomes of the unbalanced three-phase system? By the end of this topic, we are going to cover the following: types of imbalance, causes of imbalance, analysis of unbalanced delta load, analysis of a star load with neutral wire. These topics will be covered in this video, video number 10. I call it part number 1. So part 2 will include analysis of a star load with neutral wire has an impedance, and the analysis of a star load with no neutral. Part number 3, analyzing unbalanced operation using symmetrical components. So these topics are analyzed or will be covered using MATLAB and Simulink. If you didn't watch the previous videos for the three-phase systems, let me remind you what is the balanced three-phase system. So we have three voltages. They have the same magnitude, V maximum, or we can say VRMS, and they are shifted 120 degrees. So VA of t equals V maximum sine omega t, and VB of t equals V maximum sine omega t minus 120, which is 2 pi over 3 in radian. VC of t equals V maximum sine omega t plus 2 pi over 3. And bear in mind that VA plus VB plus VC should equal 0. If it's in phasor form, you can write it as V angle 0, V angle minus 120, V angle 120. And V could be RMS value. And to have a balanced system, is not only the source should be balanced, so the load should be symmetrical at the same time. So if you have a star or delta load, the impedance of the load ZA equals ZB equals ZC equals Z. Another question: what are the types of imbalance? Voltage imbalance or current imbalance? So for voltage imbalance, we have unbalanced magnitude or unbalanced phase, maybe both. For current imbalance, we have unsymmetrical loads or faults. So in these videos, part number 1, we are going to cover unsymmetrical loads, and part number 2, we are going to continue in unsymmetrical loads, but part number 3, we are going to cover unbalanced magnitude, phase, or both. Now we are going to focus on current imbalance. We can say by another way, unsymmetrical loads, where ZA not equals ZB not equals ZC. So we have 4 configurations here: delta load not balanced, star load with neutral wire, star load with neutral wire has an impedance, star load with no neutral wire. So bear in mind, in all of these configurations, the source voltage is balanced, but the load is not balanced. In this video, video number 10, we are going to cover delta load, star load with neutral wire. In video number 11, we are going to cover star load with neutral wire has an impedance, star load with no neutral wire. Unbalanced delta load. As we can see here, we have 3 impedances. They are not equal, but the source voltage is balanced. So we are going to solve this circuit per phase. So we are going to have phase A, VAB applied to ZA, so we can calculate IA, and the same for B and C. So in this case, we are going to have IA equals VAB over ZA, IB equals VBC over ZB, IC equals VCA over ZC. So that one is phase voltage equals line voltage for delta, but if the source is star connection, so that one is the line voltage of the star connection. So for the line currents, I capital A equals IA minus IC, and I capital B equals IB minus IA, and I capital C equals IC minus IB. Regarding the power, so the power of the source equals the power from phase A plus phase B plus phase C. So the difficulty here that we need to solve the problem 3 times. So we are going to do the calculations for each phase. But the problem is straightforward. We're going to solve the problem per phase, and then we're going to find the power per phase, and then we're going to add them together. Let us take an example, example number 6 in the three-phase course. For the three-phase network shown in the figure, the RMS phase voltage is 220 volts. So line voltage equals phase voltage in the delta connection. So we need to calculate the phase currents, line currents, and the supply power, P, Q, and S. If we look for the load is not symmetric, where ZA is not equal to ZB is not equal to ZC. We have the loads in polar form. For phase A, 20 angle 60 degrees, so we can convert it to rectangular form, and the same for phase B, and ZC is just a pure resistance 10 ohm. So what is the solution? We are going to solve the circuit per phase. So we have phase A, the voltage VAB equals 220 angle 0. We are going to assume that the angle of the voltage is 0 degrees. We have the impedance ZA, so we can calculate the current. IA equals VAB over ZA. So the current is 11 ampere angle minus 60 degrees. So the current is lagging the voltage by 60 degrees. What about the power? The power for this phase equals V phase I phase cosine phi. So if we substitute for that one, 220 multiplied by the current 11 ampere cosine 60, that one is 1.21 kilowatt. Or we can calculate it using I square R. So the current is 11 ampere, 11 square, and the resistance is 10 ohm. Look here. So the resistance is 10 ohm. We can do the same for the reactive power. So reactive power equals V phase I phase sine phi sine 60. So we have this value. For the apparent power of this phase, either you calculate it by V phase I phase or root P square plus Q square for this phase. What about phases B and C? For phase B, we have voltage 220 angle minus 120 and ZB equals 20 angle minus 60 degrees. So for the current, VBC over ZB equals 11 ampere angle minus 60 degree. The same like phase A, but the current is leading the voltage in this case by 60 degrees, not lagging. So how to calculate the power? The power of this phase, V phase I phase cosine phi, give you the same answer like phase A, 1.21 kilowatt. But regarding the reactive power, V phase I phase sine phi, that one is capacitive element. Look here. So we have minus 2.1 kilowatt. We can calculate it as I phase square XC. So that one 11 square multiplied by minus XC give you the same answer. For the apparent power will be root P square plus Q square or V phase I phase. For phase C, we have the voltage 220 angle 120 degrees and resistive load 10 ohm. So the current, phase current will be 22 ampere angle 120. So the current and voltage are in phase in this case. What about the power? So the power equals 220 multiplied by 22 cosine 0. So equals 4.84 kilowatt. Definitely the reactive power for this phase is 0 and apparent power equals active power in this case. What about the source power? So the source power equals power in phase A plus power in phase B plus power in phase C. So PS equals 1.21 plus 1.21 plus 4.84, 7.26 kilo. For the source reactive power, we have Q source equals QA plus QB plus QC. So for phase A, we have positive 2.1. For phase B, we have negative 2.1. And definitely phase C equals 0. So that one is going to cancel each other. We have 0 var from the source. Regarding the apparent power, so that one is root P square plus Q square. So that one gives you apparent power equals active power in this case, 7.26 kilovolt ampere. Or you can calculate it as SA plus SB plus SC, VAB IA conjugate plus VBC IB conjugate plus VCA IC conjugate. In this case, you are going to find the same answer. What about the line currents? So the line current, I capital A equals IA minus IC. So that one gives you a magnitude of 33.13 ampere, but with the same angle like IA and IB. So I capital B equals IB minus IA. So they are going to cancel each other. So that one will be 0 ampere. There is no line current in phase B. But for phase C, we have a line current equals 33.13 angle 120 with the same phase for I small c. Let's look for the phasor diagram. We have voltages 120 degree apart. Regarding I small a and I small b, they are 60 degrees and the current is 11 ampere. But I capital A with 60 degrees but 33.13 ampere. I small c is 22 ampere and I capital C is 33.13 with angle 100. So definitely the system is unbalanced and these are the distribution for the voltages and currents. Voltages are balanced but the currents are not balanced. Let us confirm these results using Simulink platform. So we are going to build the model and check the phase and line currents in this case. This is a Simulink model we would like to build for the unbalanced delta load. So we have a three-phase source here as we can see feeding unbalanced delta load. So let's look for the source. We have a three-phase source here. I built it as a star connection. So we need it as a delta. So I'm going to modify that one. I explained that one before in the previous videos. So we have a voltage here, phase voltage 220 root 2 as a peak amplitude. to have line voltage of the delta, which is a phase voltage, at the same time. So we need to divide that one by root 3, where VAB will be 220 exactly. But 220 to have it with angle 0, so we need to shift that one by minus 30 degrees, because you know for the star correction, line voltage leads the phase voltage by 30 degrees. We are going to do the same for phases B and C. Going to the load, I explained to you before how to add an image, how to create a subsystem. So for the load now, we have 3 loads. We have current measurements for the phase, for the line, and voltage measurements as well. So let's look for the load number 1. We have a resistance 10 ohm, and we have reactance, which will be 20 sine 60 degrees. So that one will be something like 17.32. So that one as XL equals 10 root 3. But I need that one in terms of inductance in Henry. So 10 root 3 divided by omega 2 by F. For the second one, phase B, we have the same resistance 10 ohm, but XC equals 1 over omega C, so the capacitance C in farad equals 1 over XC multiplied by omega 2 by F multiplied by 10 root 3, and the third one is a pure resistance 10 ohm. So let's run. Let's look for our measurements. We have the line current 33 ampere for phase A, 33 ampere for phase C, 0 for phase B, and that one matches what we get in our calculation. So the angles is minus 60 and 120. For phase currents, 11, 11, 22 with the same angles. Line voltages are balanced, 220 angle 0, minus 120 plus 120. What about the power? So the power P, 7.26 kilowatt, which equals at the same time the power S, 7.26 kilovolt ampere, and the reactive power of the source is 0. If I like to know the power P, Q, and S for each phase, we can detail it here. We measure the power for each phase, and that one shows to you how to find P and Q for each one. So the results from this model matches 100% our calculation. So now we can return back to our slides. The second type of the current unbalance, unbalanced star load with neutral wire. And take care, I said with neutral wire. Look for the circuit here. We have a star load where ZA is not equal to ZB is not equal to ZC. We have a neutral point for the load, capital letter N. And this load is fed from balanced source where VA equals V angle 0 and phases B and C have the same magnitude and shifted 120 degrees with the neutral point small letter n. So in this case, the source voltage is balanced and the potential of point N equals the potential of point capital letter N. So how we are going to solve the circuit in this case? Identical to unbalanced delta load, we are going to have 3 circuits. So we have VA applied to ZA and VB applied to ZB and VC applied to ZC. So in this case, the currents are IA equals VA over ZA, IB equals VB over ZB, IC equals VC over ZC. So the problem is easy, but the difficulty here that we need to solve the problem 3 times. What about the neutral current? So the neutral current equals IA plus IB plus IC. If we have an appreciable value for the neutral current, this means that we have unbalanced load, and that one is an indication for the unbalance. What about the power? The power PS equals the power in phase A plus power in phase B plus power in phase C. And the same for the reactive power. How to calculate the apparent power? For the source, root PS square plus QS square, or VAIA conjugate plus VBIB conjugate plus VCIC conjugate. Let us take an example. For the 3-phase network shown in the figure, the RMS voltage is 220 volt 50 Hz. We need to calculate the phase current, neutral current, and supply power P, Q, and S. It's obvious that this load is unbalanced because we have in phase A capacitive load minus J20 and phase B 6 plus J8 resistance and inductance, and phase C will be inductive load as well 14 plus J14. So we are going to put the impedance ZA, ZB, ZC in both a polar form and rectangular form, and then we are going to solve the problem. For phase A, we have the voltage applied to this impedance 20 minus angle 90 degrees because that one is pure capacitive. So the current in this case will be 11 ampere angle positive 90. So the current is leading the voltage by 90 degrees. Regarding the power in this phase, definitely active power is 0. Reactive power, we can calculate it as I phase square XC, and the apparent power equals the reactive power in this case. Please note, because that one is a capacitive load, so the reactive power should be negative, minus 2.42 kilovar in this case. For phases B and C, we are going to do the same, that the phase B voltage is 220 angle minus 120, and the impedance for phase B is 6 plus J8, which is 10 angle 53.13. So the current is VB over ZB equals 22 angle minus 173.13 ampere. So the current is lagging the voltage by 53.13 degrees. So this angle is between this current and this voltage. So what about the power? Power is V phase I phase cosine phi, or we can use I square R, so it's up to you. So in this case we have the power 2.9 kilowatt, and regarding the reactive power, V phase I phase sine phi or I phase square XC. So S equals root PB square plus QB square or V phase I phase. If you need the angle of the S, you need to multiply V phase I phase conjugate. For phase C, you are going to apply the voltage 220 angle 120 over the impedance ZC, which is 14 plus J14, which equals 19.8 angle 45 degrees. So the current is 11.11 angle 75 degrees. Again, the current is lagging the voltage by 45 degrees. This is the angle between this current and this voltage. So the power for phase C is 1.73 kilowatt, which should equal to the power 1.73 kilovar, because the angle is 45 degrees. So in this case, S equals either root BC square plus QC square or V phase I phase for this case. Now it's time to calculate the source power. For the active one, we are going to add the power from each phase. So 0 plus 2.9 plus 1.73 give you 4.63 kilowatt. Regarding the reactive power, you are going to do the same, but you need to consider the sign. So the reactive power for phase A is negative. For phases B and C is positive. So QS is 3.18 kilovar. Regarding the apparent power, S for the source is root PS square plus QS square, or you can calculate it as VA IA conjugate plus VB IB conjugate plus VC IC conjugate. So now what about the neutral current? The neutral current is IA plus IB plus IC. So if we add these three currents together, they didn't tend to zero. They have a value 27 ampere angle 134.8 degrees. And that one is an indication that our system is unbalanced. So if you notice here, the neutral current is 27 ampere roughly, while phase A current is 11 ampere. So it's obvious that one is severe unbalance. So if we look for the phasor diagram, we have the three voltages here shifted 120 degrees, VA, VB, VC, but the current IA with angle 90 leading the voltage. IB is lagging this voltage by 53.13 degrees, and IC is lagging this voltage by 45 degrees. And the neutral current is 134.8, so that one is 134.8, and the value is 27 ampere roughly. Now it's time to confirm our results using Simulink platform. So let's go. This is a system we'd like to simulate. We have a source feeding unbalanced star load. The neutral point of the source is connected to the neutral point of the load. Let's click on the source first. We have three-phase source star connection. So we are going to look for phase A, for example. We have 220 root 2 and the angle is 0.50 Hertz. Regarding phases B and C, they are the same magnitude but shifted 120 degrees. So let's look for this point. That one is the neutral point of the source, grounded. So we are going to take here output. So we have three lines and we have three currents here, meters. So these are phase A, phase B, phase C. And we have the fourth line here, which is the neutral point of the source. Let's go to the load. For the load, we are going to have three lines input to that one. Current measurements. Phase current is the line current in the star connection. And then we are going to have the measurements for phase voltages. And then we are going to adjust the three loads. For phase A, we have a pure capacitance. But we cannot put in the MATLAB pure capacitance because the MATLAB does not accept capacitor connected in parallel to a voltage source. So we are going to choose a very small resistance, as I explained before. So we put that one RC circuit, and the capacitance here will be C equals 1 over XC multiplied by omega. And in this case, XC equals 20. Regarding the phase B, we have resistance 6 ohm and inductance 8 over omega. For phase C will be 14 plus J14. So that one is the resistance 14 ohm, and 14 over omega gives you the inductance of this phase. Please look here that we have the neutral point of this load. So we are going to put a meter here to measure the neutral current. I'm not going to add the current in phases A, B, and C. I'm going to measure the current of the neutral. And this point will be the fourth line, will be connected to the line or the fourth line in the source, which is the neutral point of the source. So if you look here, that one is the neutral from the source connected to the neutral of the load. So let's run. Now we can check our results. We have the current 11 ampere of phase A, 22 ampere of phase B, 11.11 for phase C with angles 90 minus 173 and angle 75. Now 100% matches our hand calculation. For the voltages, that one is definitely 220 angle 0 minus 120 plus 120. For the power, we calculated the total power is 4.6 kilowatt, 3.2 kilovar, 5.6 kilovolt ampere. If we look inside this block, so we are going to measure the power for each phase using this block. So here we can have 0 power for phase A and we have minus 2.4 kilovolt ampere reactor. Can do the same for phases B and C. About the neutral current, as I mentioned, I'm not going to add IA plus IB plus IC in the simulation. I'm going to measure it. When I measured the neutral current, I find it 26.9 ampere angle 134.3, which matches 100% the calculation. So now we can return to our slides. So in this video, we cover two types of current imbalance. The first one is unbalanced delta load, and the second one is unbalanced star load with neutral wire, where the neutral point of the source is connected to the neutral point of the load and the neutral point of the source is grounded. So they have the same potential. So to solve the problem here, we are going to solve the circuit per phase, and then we are going to add the values from phase A to phase B to phase C to find the power. What will I watch in video number 11? In video number 11, we are going to cover another two types of current imbalance. Unbalanced star load with neutral wire impedance and without neutral wire. See you in the next video.